All right, so we're back. I apologize for cutting the stream short. I think I jumped the gun on that one. So there was a question by Emil Rueda, so I think we'll start with that.
Okay, great, yeah. So I'll share my screen to answer that. Okay. Yeah, this is a great question. Why do low metallicity stars have smaller radii? So there's actually two things that are contributing to this plot here that's showing that low metallicity stars have smaller radii. One is the effective temperature. So the effective temperature is just the temperature at the tau equals 1, or like the optically thick surface of a star. And low metallicity stars emit more of their light at bluer wavelengths just because of the opacity in their atmosphere. So even just looking at this, you can kind of see that the solar metallicity stars have a bit less flux here, whereas the subdwarf or the lower metallicity stars are emitting a bit more of their light at bluer wavelengths. And so that means that these stars don't have the same mass. So for example, this star here and this star here do not have the same mass. This star has the same effective temperature of this star, but this star probably has a mass a lot more similar to some of these solar metallicity stars. So it's just the bigger effect is that the temperatures of these stars, when we calculate them, they're a lot higher than for a solar metallicity star. And that's just because of the opacity sources in their atmosphere and where this tau equals 1 surface is hit. And then the second effect, which is smaller, there is a bit of an effect for a given mass. Do we have the same radius of these stars? And low metallicity stars do have a slightly smaller radius for a given mass, we think. But this is a much smaller, like 5 to 10%, whereas not like a factor of 5. And this is just because hydrostatic equilibrium for this atmosphere is reached at a lower radius than it is for a solar metallicity star. So it's a combination of these two effects. So I think that this plot, oftentimes you think temperature scales directly with mass. So this star and this star have the same mass and one of them is just 5 times bigger. It's a little bit misleading because these stars don't have the same mass at all. Okay, so now I wanted to talk about how we can use abundances to learn about planets. So before I told you via this high-resolution cross-correlation technique, we found all of these different elements and molecules, but we didn't really talk about why is this important. And so now that we've talked about abundances and what are some of the applications of knowing an abundance, I wanted to go back to elemental abundances in planets. And elemental abundances in planets are thought to trace different planet formation pathways. So an example of this is for directly imaged planets. So here's a nice, this is such a cool GIF, but this is, we can like actually see planets around HR 8799 moving in time. So these planets are directly imaged. And a lot of the planets that are directly imaged, in order to actually see them, these planets have to be pretty massive and pretty bright. So they're kind of on the edge of what we call, or they're on the edge of brown dwarfs and planets. So we want to know in binary star systems, when two stars collapse, they basically collapse out of the same gas and dust. And then they are close to each other and are in a binary pair. But in a planet, we would expect it would form in the disk of the star. So as the star is forming, it has this disk of gas and dust. And then a planet would form via core accretion, so accreting different things in this disk. And for these objects that are kind of on the edge of being planet size or brown dwarf size, we don't know if they've formed in a disk like a planet or like a star. And what we think would be a diagnostic way to tell the difference is to look at their metal abundances. So an object that formed like a star should have formed out of the same material as a star, and therefore should have the same overall metallicity as the star would have. The companion would have the same metallicity as the star would have. But for an object that formed in the disk, it should be enhanced in heavier elements like oxygen and all metals, because the metals are the things that kind of form into pebbles and stuff and start to form the planets. And so this is something that we're kind of on the edge of being able to do. So we haven't really been able to do this yet, but this is kind of like future and what we hope to be able to do with a lot of these directly imaged planets. So another cool thing that you can do with abundances is you can look at abundances in protoplanetary disks. So these disks that are forming stars. And here's a nice spectrum from a high-resolution spectrograph. This is CryRes. It has a resolution of 96,000, and this is looking at the carbon monoxide line. So before we were looking at the carbon monoxide line at 2.3 microns. Now we're looking at the carbon monoxide line at 4.7 microns. So this is the carbon monoxide 1 to 0 line, whereas before we were looking at the 2 to 0 line. So this is kind of the main carbon monoxide line. And these lines are in emission. So normally we look at lines in absorption, but we're looking at a protoplanetary disk and we're looking at the emission from the protoplanetary disk. So here are our carbon monoxide lines resolved at high resolution. And we can resolve the velocities and the velocity shifts and the ratios of different lines in order to tell where in the disk these carbon monoxide lines are being emitted, and at what temperature the gas is that's emitting these lines. And this paper from 2015 found that carbon monoxide was emitting in two different spaces, one kind of closer to the radii of, one kind of closer to the stellar, to the star, and one a bit farther out. And this depended on the mass of the star. And so by looking at these lines in the disks, we can kind of start to see where different gases and dust are and where planets are going to form. So kind of looking at this in a more theoretical way, we expect the protostar in a disk to be at the center. And as we move farther out, less of the protostar's light is hitting these places. And so cooler and cooler things can start to condense. So very close to the central star, the only things that can condense into planets are metals and minerals. But as we get a bit farther out, carbons and silicates can start to condense out here. And as we get even farther out past a snow line, we can start condensing molecules such as water or methane or ammonia. And so based on where the planet formed in the disk, we think that it should have different fingerprints of different abundances. And so by looking for the carbon to oxygen ratio or the nitrogen to oxygen ratio, we'll be able to tell where different planets formed. And this is really cool because we don't know where these hot Jupiters come from. It's not thought that hot Jupiters form this close to the star. It's thought that they form farther out and then migrate in. And also the carbon to oxygen ratio and the nitrogen to oxygen ratio can help us see where the planet formed and when it evolved. If it migrated in when the disk was still there, then it should have some of the signatures of migrating through the disk. But if it formed and then migrated later, it shouldn't have any of the signatures of migrating through the disk. So by measuring carbon to oxygen ratios and nitrogen to oxygen ratios, people are hoping to be able to discover where these exoplanets are born, and then you can kind of back out how they evolve over time. And this is another kind of area that we're just starting to be able to do. And with telescopes such as James Webb and others coming soon, I think that we'll have a much clearer picture as to how much these carbon to oxygen ratios can tell us, and start to see maybe get more information about how these planets are forming. Okay, so this is all of the lecture that I have for this last day. And then next I was going to do, like we've been doing before, the Kahoot quiz. So, okay, let me actually just check to make sure I don't make the same mistake as yesterday and have some with 20 seconds. Oh, I already found one with 20 seconds. Good thing I checked. Okay, it all looks good now. So let me share my screen. Okay. Great. So you can see the game pin, it's 1642964. Okay, so I'm just going to wait a few more seconds, see if anybody else joins. Okay, I think 16 seems like a lot of people, so we'll just start. Okay. True or false? If an exoplanet has water in its atmosphere, the transit depth will increase at 1.4 microns, where water has absorption. Okay, great. Yes, most of you got this. The transit depth is just how big it correlates to how big the exoplanet is. So a larger transit depth means the exoplanet looks bigger, and the exoplanet would look bigger where water is absorbing, because you'll get kind of the cloud where water is will make the atmosphere bigger or look bigger at that wavelength. Okay. All right, next. This plot shows an exoplanet observed at high resolution. Which lines are from the planet? So are the white lines from the planet, the black lines from the planet, or neither, they're both from the star, or are both from the planet? Okay, great. Most of you got this one, but the white lines are from the planet. So when you're actually observing an exoplanet at high resolution, you can actually see the lines of the planet. Whereas when you're detecting radio velocity exoplanets, you're just looking at the star and detecting the wobble. But when you're observing the transits or the emission spectrum of the exoplanet, you actually are able to directly resolve the lines of the planet. Okay, next. What does the blue line show in this plot? A cross-correlation detection of an exoplanet's emission, a cross-correlation detection of an exoplanet in transit, the spectrum of an exoplanet's emission, or the spectrum of an exoplanet in transit. Okay, great. So again, most of you got this. We know it's cross correlation and not the spectrum because the x-axis had radial velocity and not wavelength. And we know that this is in transit because the phase that we're covering is right around phase 0. And so that's when the exoplanet is transiting in front of the star. All right. If an absorption line is not saturated, an increase in the equivalent width by a factor of 4 results in a decrease in the abundance by a factor of 2, an increase in the abundance by a factor of 8, an increase in the abundance by a factor of 4, or an increase in the abundance by a factor of 2. And this is for a line that's not saturated. Okay. Yeah, so if the line is not saturated, the change in equivalent width directly corresponds to the change in abundance. So you get an increase if we have an increase in the equivalent width, we'd have an increase in the abundance by a factor of 4. Okay, true or false? Directly after the Big Bang, the universe only consisted of hydrogen, helium, and a small amount of lithium. Yep, so directly after the Big Bang, it was just hydrogen, helium, and a very little amount of lithium. And it wasn't until we got stars creating the heavier elements that the universe started to have and galaxies started to have different metals. What does the iron fraction, why does the iron fraction increase over time? Is it because iron is created by low mass stars over time? Iron is created by supernovae over time. Iron is created in black holes, or iron is created by nuclear fission. Okay. This question I think was a little bit mean because iron, you had to remember kind of the exact square. But hopefully, most of you knew that it was either created by low mass stars or supernova. And most of the iron is created by supernovae and not by dying low mass stars, type 1a supernovae, or by massive stars. Yeah, that was kind of mean. Sorry about that. Okay, true or false? Low metallicity stars are older than high metallicity stars. That's actually true. So a star that has a low metal content, so low iron, is older than stars that have high metal content. So stars that are born more recently, they were born when the metal content of the galaxy was a lot higher, because there's been more time for supernovae and low mass stars and high mass stars to enrich the gas and the dust that these stars are formed out of. And so if the star has a low metallicity, then you know that it has to be a pretty old star. Okay, true or false? Metal-rich stars are less likely to host hot Jupiters. Great. Okay, most of you got that. So metal-rich stars are actually more likely to host hot Jupiters than metal-poor stars. Okay. If the metal abundance of a large directly imaged companion is found to be the same as the host star, what can we say? Can we say that it's likely to be habitable? Can we say that it's likely it formed in the disk of the star via core accretion? Is it likely that it's not gravitationally bound and not actually a companion? Or is it likely to form like a star or like a binary? Okay, that one was a bit tricky, so I can go over this again later if we need to. So if the metal abundance of the companion is the same as the host star, it probably formed like a binary system. So it formed like a star. So what that means is they both collapsed out of the same gas and dust. So then they should have the same metal content. If it formed in the disk via core accretion, then we would expect it to have more metals and heavy elements, oxygen, water, methane, those type of things, because it would have accreted those as it formed. So it should be more metal enhanced if it formed in the disk. If it has the same metallicity as the host star, we think that this means that it formed like a star. Let me know if you want me to go over the slide of that again. Okay. If a planet formed interior of the water's snow line, it's most likely made of, so interior, inside, it's not it's inside of the snow line? Is it most likely made of metals and minerals, methane ices, water ices, or is it only made of hydrogen? So inside of the snow line. Okay, great. Most of you got this. If it's inside of a snow line, then it shouldn't have many ices. So it shouldn't have the methane ices or the water ices. Okay. And last one. A star that has a Fe/H of -1. A star has an Fe/H of -1. What does that mean? Does it mean the iron or Fe abundance is 1/10 of the hydrogen abundance? Does it mean the iron abundance is 1 less than the hydrogen abundance? Does it mean the iron to hydrogen ratio is 1/10 the solar iron to hydrogen ratio? Or does it mean the iron to hydrogen ratio is 1 less than the solar iron? Oops, that's supposed to say Fe. Fe/H ratio. So this is just about what the Fe/H nomenclature means, which I always think is so confusing. Okay, great. You all got that. Yeah, so it means that the iron to hydrogen ratio is 1/10 the solar iron to hydrogen ratio. All right, that was the last question of the last quiz. Okay, that was really great. And I will stop sharing now. So that's all I have for this session. Are there any questions? I don't see any yet.
All right. I won't cut the stream yet, so there's time enough for a few questions.
Yeah, and also while you think of your questions, or I can quickly say what we'll be doing for the next session. So I did send a document for the final workshop to the email. So hopefully you all got this, but let me just share it so you know what it should look like, to check if you've gotten it. Okay, so it should look like this. And again, we'll be using the co-laboratory notebooks. And we're going to be using data from Apogee, which is some of the spectra some of the results I talked about today were from Apogee. So it's resolution 22,000 spectra, and they cover the H band, so the near infrared, about 1.5 microns. And I've downloaded the spectra because the Apogee website is a little bit difficult to navigate. And I put it in my GitHub folder, so you can just download this from my GitHub folder, so you don't have to navigate downloading things from the Apogee website. Okay, so yeah, that's what we're going to be doing after break. And I was kind of hoping that this would not take that long, just to have it take the first session. And then for the second session, I was thinking that maybe some of you would have questions or wanted to talk about my research, or any other questions about grad school or postdocs or any other astronomy related questions. You're welcome to ask me in that second session. And I also made a little collage of some of you sent photos of or screenshots of the work that we've done. So if you still want to send me any screenshots, I can add them to show off how awesome plots you guys all made. Okay. I don't see any questions now, so I guess we can just end a few minutes early, and if they have questions, they can just come back and ask them in the next session.
All right, so should we start at the scheduled time, or should we?
Yeah, maybe like just 5 minutes early would be good, just to make sure we have enough time for the. I tried to make it shorter than yesterday, so hopefully it'll fit in the first session.
All right, so that means, let me just check to make sure. So that would mean 10:20.
Yes.
Starting at 10:20. Right. Okay, so I'll next session I won't be here. It will be Esteban again. So thank you, Aurora, and thank you all. So I think there will be plenty of questions about your research later on. So that's good. Okay, thank you all.